Hello everyone, my name is James D. Mondelo, your next reporter. So in this part of our lesson, we are going to discuss about the processing of fiber reinforcement sheet. So in this part of the lesson, we will going to discuss what are the three types of processing of fiber reinforcement. So in processing of fiber reinforced composites, to fabricate continuous fiber reinforced plastic that meet design specification, the fibers should be uniformly distributed within the plastic matrix. As you can see in the screen, there are three types of processing of fiber reinforced composite. The number one is pultrusion, which is having continuous length and a constant cross-sectional shape. Number two, the prep-preg production process, industry's term for continuous fiber reinforced pre-impregnated or tape form. And lastly, number 3, filament winding, process by which continuous reinforcing fibers are accurately positioned to form a halo. So as you can see in the screen, it shows the schematic diagrams of the pultrusion process. So pultrusion is used for the manufacture of components having continuous lengths and a constant cross-sectional shape. So an example of this is rods, tubes, and beams.
What is pultrusion? Pultrusion is a manufacturing process for producing continuous lengths of fiberglass reinforced plastic shapes with a constant cross-section. While pultrusion machines vary in design, the process is basically the same. Let's first start with the fiberglass reinforcement. Creels of unidirectional roving provide longitudinal tensile strength, or the strength along the length of the profile. Rolls of continuous filament mat, woven roving, or stitch fabric provide the profile with its transverse properties or its strength across the width of the profile. All reinforcements are first fed through preforming guides that will begin to shape the raw glass fibers into the finished profile. The glass is then pulled into a resin bath that saturates or wets out the reinforcements. The resin bath contains a mixture of resin, most commonly polyester or vinyl ester, pigments to add color, filler to enhance properties, and a catalyst to aid in curing or to turn it from a liquid to a solid. Surfacing veil is added to give the profile a resin-rich surface and enhance the appearance of the final product.
Now let's proceed to the schematic diagrams of the prep-preg production process. So prep-preg is the composite industry's terms for continuous fiber reinforcement pre-impregnated with a polymer resin that is only partially cured. This material is delivered in tape-shaped form to the manufacturer, which then directly molds and fully cures the product without having to add any resin.
Pre-preg is a common term for reinforcing fabric which has been pre-impregnated with a resin system. Our pre-impregnated resin system already includes the proper curing agent. The pre-preg comes to you ready to lay into a mold without any additional resin or hardener. Pre-pregs feature the perfect amount of resin, which is their real advantage. With a traditional hand layup, it's difficult for fabricators to achieve the perfect weight ratio of resin to fabric. Typical hand laminates, even when vacuum bagged, end up with excess resin, which compromises the strength of the laminate.
The last one is the filament winding. So these filament winding are composed of helical winding, circumferential winding, and polar winding. So filament winding is a process by which continuous reinforcing fibers are accurately positioned in a predetermined pattern to form a halo.
Filament winding machines typically are computer numerically controlled and have between 2 to 7 axes of motion. The mandrel is usually suspended horizontally between a headstock and tailstock. A carriage travels lengthwise at speeds synchronized with mandrel rotation, delivering the tow from a wind eye at a selected angle. A winding comb, or a series of rollers, collimates several strands of tow into one bandwidth for placement on the mandrel. This tow is applied either wet or dry.
Now, the next part is the structural composites. So So normally composed of both homogeneous and composite materials, the properties of which depend not only on the properties of the constituent materials but also on the geometrical design of the various structural elements. So the first structure of composite is the laminar composite. So to sum up the definition of it, laminar is a two or more layers bonded together in an integral piece. So an example of this is plywood, in which layers are the same wood but grains oriented differently to increase the overall strength. Applications that use laminate composite are primarily in aircraft, automotive, marine, and in building or civil infrastructure sectors. So the picture shown is the schematic diagram of the laminar composite. So it's figure 9 layups for laminar composite. So letter A, which is the unidirectional, letter B, which is the cross ply, letter C, the angle ply, and letter D, the multidirectional. Next is the sandwich panels. So a sandwich panel consists of two outer sheets or faces that are separated by and adhesively bonded to a thicker core. The outer sheets are made of a relatively stiff and strong material, typically aluminum alloys, steel and stainless steel, fiber-reinforced plastics, and plywood. They carry bending loads that are applied to the panel. The core material is lightweight and normally has a low modulus of elasticity. And this is the schematic diagram showing the construction of a honeycomb core sandwich panel. So as you can see, it consists of two face sheets, and at the center is the honeycomb which bind the two face sheets. And the last part of my report is all about the nanocomposites. So composed of nano-sized materials or nanoparticles that are embedded in a matrix material, designed to have mechanical, electrical, magnetic, optical, thermal, biological, and transport properties that are superior to conventional filler materials, and these properties can be tailored for use in specific application. An interesting and novel phenomenon accompanies the decrease in size of a nanoparticle is dramatic changes in physical and chemical properties. So nanocomposite matrix materials may be metals, ceramics, and polymers, but the most commonly used are the polymers. So for these polymer nanocomposites, a large number of thermoplastic, thermosetting, and elastometric matrices are used. The properties of nanocomposite depend not only on the properties of both matrix and nanoparticle, but also on nanoparticle shape and content as well as the matrix. Most of today's commercial nanocomposites use three general nanoparticles types. Number 1 is the nanocarbons, number 2 is the nanoclays, and number 3 is the articulate nanocrystal. So these nanocarbons, defined as a carbon materials with a size or structure in the nanometer scale, are now one of the central topics of both the academic and industrial community. Fundamentally, nanocarbons can exist in 0, 1 or 2-dimensional space, which provides in-depth understanding into the bonding behavior and arrangement of carbon atoms and the construction of 3-dimensional nanocarbon architectures. The second one is the nanoclay. So nanoclays are clay minerals optimized for use in clay nanocomposites, multifunctional material system with several property enhancements targeted for a particular application. So nanoclays are a broad class of naturally occurring organic materials. So according to our module, these are the applications of nanocomposites: the gas barrier coatings, energy storage, flame barrier coatings, dental restorations, mechanical strength enhancements, and electrostatic dissipations. But then I searched on the internet, and these are the nanocomposites, their uses and applications. So the first one here is producing batteries with a great power output, and then speeding up the healing process for broken bones. So researchers have shown that the growth of replacement bone is speeded up when a nanotube polymer nanocomposite is placed as a kind of scaffold which guides growth of the replacement of the bone, followed by producing structural components with a high strength to weight ratio. For example, an epoxy containing carbon nanotubes can be used to produce nanotube polymer composites windmill blades. This results in a strong but lightweight blade, which makes longer windmill blades practical. These longer blades increase the amount of electricity generated by each windmill. And then, making lightweight sensors with nanocomposites, using nanocomposites to make flexible batteries. So a nanocomposite of cellulose materials and nanotubes could be used to make a conductive paper. When this conductive paper is soaked in an electrolyte, a flexible battery is formed, and then making tumors easier to see and remove. So researchers are attempting to join magnetic nanoparticles and fluorescent nanoparticles in a nanocomposite material that is both magnetic and fluorescent. The magnetic property of the nanocomposite particle make the tumor more visible during an MRI procedure than prior to the surgery. The fluorescent property of the nanocomposite particle could help the surgeon to better see the tumor while operating.